Let's go through Activity 11, Association Rules. So the data that we have are receipts from 75,000 transactions at a chain of bakeries. So they sell baked goods, they sell some drinks, and we want to use the data to do some sort of market basket analysis. We want to figure out what combinations of items tend to be purchased together, and then really what to do with that sort of information. So the first step of any market basket analysis is to get the data into a form that we can use the A-rules package with. So in this case, we have two different data sets, and we're going to want to make sure to read them in the appropriate manner. So receipts, I'm going to use the general command read table. The data file is receipts.csv. Now, read table is like CSV, but it gives you a little bit more flexibility in how the data is actually stored in that file. So in this case, one thing is that there are no header names for the variables. They're just presented raw data with nothing to really tell us what that is. So we'll do head equals false. We'll use separation between fields equals a comma. And then what we're going to do is add in the strings as factors argument for false. Because when we're reading in these receipts, we don't really want to have the text fields be saved as categorical variables. They're just text. We don't need them as factors. So let's read in the receipts, and the product list is saved in more or less the same way. So we're going to read in the data file with the same set of arguments here. And if we just get a little bit of a preview, what does the receipts data frame look like? Well, it's ID column here for V1, the very first column, and then a bunch of ones and zeros for the products that were appearing in that transaction. So we have a little bit of a key that talks about, all right, chocolate cake, lemon cake, casino cake, etc. That's what the actual names of the columns are in the receipts data frame. All right, so we need to work with the data to get into a form that we can actually use the A-rules package with. So the first thing that we're going to do is to take the transaction ID out of the receipts data frame. So we're going to create a vector called ID, which is just going to be the V1 column of the receipts data frame. These are essentially the identities, the cart numbers of our transactions. And then we're immediately going to take out this column from the receipts data frame. And this is because we need to make sure that our receipts data frame just contains item information, whether or not items were or were not in that transaction. All right, so now we're going to take the products data frame and take out the V2 column, basically what the names of all these products are, and we're going to store that into a vector called item. When we put all this stuff together, we're going to be able to basically figure out what items were in each transaction. So what I'm going to do is I'm going to minimize those arrows, and I'm going to go ahead and just run my item command. And now what we're going to do is to change the type of object that receipts is. Currently it's a data frame. We want to make it a matrix because that's the way that we're going to be able to convert that into a transactional object. So we're going to left arrow into trans the result of running the command as dot matrix. Basically take this object, but forget what type of object it currently is and treat that as a matrix. And what we want to do is we want to give the rows and the columns of trans names. Basically, we want the rows to be named ID, so it labels each transaction, and we want the columns to be called item, because those ones and zeros were corresponding to whether or not they had or did not have that item in the transaction. So once we have our data, a bunch of ones and zeros as a matrix, the rows are labeled, the columns are labeled, then we can use the as command to convert that matrix into something that we can work with, a transactional object. So we'll resave trans into or run the conversion and resave that back into trans, so that now if we were to look at the first 5 transactions, we can see that, all right, it looks like the first receipt, someone bought apple pie and ganache cookie. Second receipt had these items on it. And now we're ready to find some sort of an association rules. What combinations of items appear together in transactions more often than what we would expect if shoppers were just picking items to purchase at random here. All right, so we need to specify the types of rules that we're interested in. Now, we can go and find all sorts of kinds of rules. It's going to be up to us to determine which ones are interesting. And in my view, an interesting rule would be one that is at least roughly widely applicable. So we need to define the support of our rule set, basically the minimum number of transactions to which we want the rules to apply. And in this case, let's say we want the rules to apply to a minimum of 50 transactions. So what that means is that our support is going to be 50 out of the total number of transactions, 50 out of 75,000. And we want the rules to be correct fairly often. We're not going to be all that excited to find a rule that applies to 1% of the time. And so we're going to go and set up our a priori command as follows. So we have our transactional data set. That's our first argument. And then what we need to do is we need to specify the parameters that we want to be using when we run the a priori command. All right, so we got to figure out how is this command set up. And what I'm going to do is I'm going to load in the cheat sheet that I had uploaded onto Blackboard as well. That's going to help me figure out how all these commands need to be specified. So I'm going to go into my association rules folder. I'm going to open up the cheat sheet here. And how do we actually make these rules? All right, so I'm going to copy and paste this into our activity and just make the required changes. All right, so the name of our transactional object is trans. Our minimum support we're going to have as 50 out of the 75,000 carts. The level of confidence, I want it to be at least 50%. I don't want to put any restrictions on the rules yet, so I'm going to take out the min-lang and max-lang parameters. I'll leave in this last one because that just prevents a lot of output being printed to the screen. All right, so we've made the rules just like that. A lot of these are going to be potentially redundant, basically more complex rules than simpler rules, but they have a lower level of confidence. So we can remove all of the redundant rules as so. And then we can see how many are left just by using the length command. How many do we have left? Oh, 116 here. So we didn't put that into Blackboard. And I guess along the way, I did want to see how many rules we started out with. So let's remake those rules. We started out with 242. Removing the redundant ones, we have about half of that. All right, so let's find the interesting rules. That 200 is, or 116 is still a lot to search through here. And so we can go and say find the 5 rules that were the most correct, that basically had the highest levels of confidence. So what we're going to do is we're going to sort our rules by confidence, and we're going to add the argument decreasing equals true because we want the higher numbers at the top. And if we were to just run this, set of 116 rules, we can actually see what they are. We always have to inspect what these rules are. This will print out all 116 to the screen. That's a lot of output. So if I just want the top 5 rules, I can go and put in some square brackets and basically refer to the first 5 rows of the results, much like referring to the first 5 elements of a vector. So there's our top 5, and what we see is that 3 of those rules have 100% confidence here. So 100% confident, 100% confident, 100% confident. So every single time a transaction had a raspberry cookie, a lemon cookie, raspberry lemonade, and green tea, it also had lemon lemonade here. All right, so we might want to know, okay, how many carts did this rule actually apply to? Well, we can use the fact that we have the value of the support, the fraction of carts to which this rule applied. If we multiply that by the number of transactions, we see that there's actually a little over 1,500 carts that this rule applies to. So it's pretty interesting. Of the 1,555 carts that had these 4 items in it, every single one of them also had lemonade here. All right, so let's move on to question number 5 now. Let's get some additional practice sorting. I'm going to copy and paste this command here. this case, we're interested in looking at the bottom 5 rules in terms of lift. So I'm going to sort by lift, and I'm going to have decreasing equals false. So that way the smallest ones are up at the top. So we're going to look at those bottom 5 here, and it looks like the one with the overall lowest lift is up on top, and then it slowly gets a little bit larger here. All right, so the lowest lift rule has this value. It involves Napoleon cake and strawberry cake. And let's actually try to interpret the number of this lift here, 5.628572. All right, so there are a few ways to interpret this value. One thing we can say is that these two items, Napoleon cake and strawberry cake, are appearing 5.6 times more often together than what we would expect if shoppers were just picking items to buy at random. Now, there's another way to interpret it, and that's what this problem is going to get at. So the first thing we're going to try to do is find the overall frequency that strawberry cake appears in our transactional data. So we're going to use the item frequency command on trans. If we just do that, it gives us the item frequencies of everything. It's not alphabetized, so it's kind of hard to work with. And so we're going to turn on the square brackets and say, all right, give me strawberry cake here, the supported strawberry cake. All right, so here we have a baseline probability for how often we should expect carts to contain strawberry cake. It looks like that, shoppers just choosing items at random here, the average shopper, we'd expect to find strawberry cake in a little bit over 9% of carts. All right, so the support of strawberry cake, the overall fraction of carts that it appears in, is 9.264%. And the lift tells us something interesting about how much this probability increases with the additional knowledge that the other item involved in this rule is in the cart. So what we do is we take the lift of our association rule, which is 5.628, etc., and we're going to multiply that by that initial probability, basically the prior probability that this item would be in the cart. And we find that this is 52%. So what this 52% is telling us is essentially what the posterior probability of finding strawberry cake in the cart, given the additional information that Napoleon cake is in the cart. So it's boosted the probability of finding strawberry cake by a factor of the lift by a factor of 5.6. And so the knowledge of Napoleon cake being in that cart has substantially changed, substantially refined our idea of how likely it is to find strawberry cake in there. All right, so this was 52% here. Make sure we got that right. And then let's go ahead and interpret this value here. So overall, the probability of finding strawberry cake in a transaction is that let's call it 3%. So inside a transaction is 9.3%. So that's support. However, given the additional information that Napoleon cake is in the cart, the probability of also finding strawberry cake is increased by a factor of the lift, 5.6, to a total of about 52% here, 52.1%. So that's another way to interpret that lift. It's basically the factor by which the probability of finding that item increases, given the knowledge that the other item is in the cart. All right, question number 6 asks us to explore making visualizations of some of these association rules. So we have a lot of rules. We don't want to try to visualize them all at once. So let's go ahead and remake the rules so that there's only a few of them for us to consider. So I'm going to go and redo our a priori command, and I'm just going to call this small. So we're still working from the transactions data, the transaction object here, and in this case we're changing the values of the support to 0.025, the confidence to 0.8, and the max length to 3 here. So I'm just going to overwrite that. We'll leave this control list verbose equals false there just so that it doesn't drown us in output. It's letting us know that only patterns up to a length of 3 were returned. So 2 items in the if statement, 1 item on the right-hand side in the then statement. And let's go ahead and make the plot here. So just plotting small with a method equals graph, and some additional parameters to make that graph look pretty. So what we're going to do is add in the vertex size of 2, the vertex label, and finally this additional argument. And we're going to take a look at the results. I'm going to make my plotting window a little bit bigger so I can make sure to see it. All right, so now we can talk about it here. One thing that I notice immediately is that, wow, we have this cluster of rules that all seem to involve each other. This is that lemon lemonade, raspberry cookie, and lemon cookie. Basically, if I inspect this really closely, what I find is that when we have any 2 of those items in a cart, it implies the existence of 1 of those other 2. So we have a bunch of kind of self-referential rules. We have other rules that are kind of just isolated from each other. So we have some rules involving opera cake, cherry tart, apricot Danish, some rules involving apple tart, apple croissant, and apple Danish here. And so we see we have small little clusters of items that seem to be related. This one big cluster is kind of interesting because we do see that hot coffee, coffee eclair, the almond twist, and apple pie have a bunch of rules that involve each other, but there's an additional set of items that is, tangentially related to one of the items in that rule set. All right, so something that we can talk about with this graph is that the items seem to be somewhat clustered. So all the rules involving that lemon lemonade, the raspberry lemonade, the lemon cookie, and raspberry cookie. So all the rules involving them involve each other and no other items, so kind of they're all 4 playing around with each other. There are other isolated clusters of items that are related, like the apple tarts, apple Danish, apple croissant, and there is a cluster of items that seem to overlap. So there's a few clusters of items that seem to overlap here. So 2 clusters involve hot coffee, 2 involve coffee eclair. And we wouldn't necessarily been able to easily identify that just by looking at a set of rules. Looking at the graph lets us know kind of quickly, what bunches of items are related to each other. All right, there's some other plots that we can make here. So we can make the 2-key plot and the grouped plots. I'm going to skip over that because I don't particularly find them all that useful for this particular context. All right, so now what do we actually do with these rules? It's pretty easy to discover a lot of them. It's pretty easy to sort them based on terms of confidence, in terms of lift, etc. But what do we actually do? Without any application, these rules are just kind of fun and interesting facts. But we're doing business analytics. We need to apply this to making intelligent decisions. So one thing is that, all right, blackberry season is coming up soon. We might like to know, are there any rules that involve, say, blackberry tart? If so, well, we can maybe craft a clever promotion to try to increase sales of blackberry tart, or maybe increase the sales of an object or an item that's related to blackberry tart. So let's go ahead and try to find a subset of our initial rules where the left-hand side or the right-hand side involves blackberry tart. So the way that I can do that is to specify, all right, I want rules where the left-hand side contains blackberry tart. I can't actually use the equal sign here. I actually have to do the percentage in. So I want the left-hand side to contain blackberry tart, or I want the right-hand side to contain blackberry tart. So I can separate that by our or symbol. And I can essentially, well, I'm saying, hey, don't inspect this. Let's just determine that there are actually no rules here by just running some commands. So I'm going to call this blackberry. I'll left arrow the result of making the subset of rules that contain blackberry tart. And I'm just going to look at the length of them. So how many rules do I have? I have 3. Well, that's kind of surprising because I thought there was going to be 0. Let me check to see what's going on here. Oh, because I was supposed to remake the rules with a different set of parameters. So, whoops, I did find 3, but I didn't pay attention to my own instructions, and that I was supposed to remake my rules to be even simpler rules than what I'd initially considered. So what did I want? I want a new set of rules whose support is at least 50 out of 75,000, so that's already there. Confidence of at least 50%, and a maximum length of 2. So I need to add in that max length equals 2 commands. I'll get a warning because it's going to tell me that the mining stopped after rules of length 2 were found. That's exactly what I wanted. That's good. So now I can go and look to see about that subset. All right, which of these rules involved blackberry tart on the left-hand side or on the right-hand side? None. So too bad. It's about to be blackberry season, but doesn't look like we can take advantage of any sort of rules that we found in our association rule mining. All right, well, what about this? Chocolate cake and chocolate coffee actually have an interesting rule going on. They have a symmetric rule set. The existence of one implies the other, and vice versa. So let's go and take a look at these rules now. Let's just inspect our rules. And we can see that here are the 2 rules in question. Chocolate coffee implies chocolate cake and vice versa. And it looks like that the level of confidence of the higher of these 2 is just 0.5296 or so. So that's the cheesy way of doing it, just actually looking at it. But I could, take a subset here. How would I do that? Well, I was going to call this subset. I'm interested in looking at the rules where the left-hand side contains either of these 2 items and the right-hand side contains the other. So if I just say, all right, well, give me the rules where the left-hand side is either chocolate cake or chocolate coffee, and then use that same vector on the right-hand side. Same item's never going to be on the left and the right-hand side, so it's basically asking, just give me these rules that have one on the left and one on the right. There's my 2 rules, and I've recovered those. So it looks like our answer here is this. And while we're at it, we can, talk about what we would actually do with these rules here. So the level of confidence with these rules is kind of small. If someone has chocolate cake, there's only about a 53% chance they're going to have chocolate coffee and vice versa. But the lift is pretty sizable. The frequency of finding both of these items in the cart is about 6.3 times higher than what you would expect if shoppers were picking items kind of at random to buy here. So this is potentially useful here. So we'd like to recommend to our boss a course of action that takes advantage of this rule and which may increase profits. Well, I think there's a pretty clear one here. Basically have some sort of buy one, get one discount. So, buy a chocolate coffee and get a chocolate cake for, let's say, 50 cents off. So about half the people are going to be buying chocolate cake anyway, so you'd be kind of throwing away a little bit of money on those type of people. But maybe that discount is all what additional people need to, buy into that extra product. So about half the people aren't buying chocolate cake when they're buying chocolate coffee. Maybe a little bit of a discount would make them do it. So we can try buy a chocolate cake and get 50 cents off a chocolate coffee promotion. You can come up with a clever name for it, like double chocolate. That's not clever, but something that would be kind of interesting. The key thing is, since we've identified that a large fraction of purchasers of chocolate cake also end up getting a chocolate coffee, well, there's something there. Let's try to make this number, this 53%, even bigger. Right now, 53% of people buying chocolate cake or buying chocolate coffee, maybe a promotion on one of those items will, increase the fraction that go for the other. All right, the last question here. The coffee shop's trying out a new product. After 5,000 transactions, it's found in 300 of them. And it looks like there's another item that's associated with the presence of this item. Bottled water tended to be found with this new item together. We might be curious to quantify their association. So bottled water appeared in 375 total transactions out of the 5,000, and it turned out they both appeared together in 37. So let's find the value of the lift. All right, well, the value of the lift, if you remember, are the fraction of carts that contain both items, so 37 out of 5,000, divided by the product of the fractions that contained each. So 300 out of the 5,000 contained this new mystery item of interest. 375 of those carts had bottled water, and so this ratio gives me the lift. All right, so 1.64, we're finding both these items together about 1.64 times more often than what we would expect if shoppers were just kind of picking items at random here. Now, the question is, all right, is this lift statistically significant? Is it possible for two completely independent items to be purchased together as often as what we're seeing here? What is this probability here? All right, well, we have a function that I've written here. And we can run this function to see, all right, well, what is the probability that shoppers, basically picking these items at random, end up having bottled water in this other product, at least 37 out of these 5,000 transactions. So we had 5,000 transactions. We found that item in 300 of them, water in 375, them together in 37 of them. And so we find that this p-value is about 0.15%. So if shoppers were just picking items at random to purchase, there's about a 0.15% chance that we would observe bottled water in this new product together in 37 or more carts. So it does look like we have some substantial evidence for an association going on. Is it statistically significant, though? Is it so unlikely by chance that we're kind of convinced there is something going on? Well, we need to compare this to our p-value threshold here. Now, the answer to whether it's statistically significant or not depends on basically how many rules we've looked at so far. So if this is the only rule that we've considered, then our threshold is 5%. Anything less than 5% for a p-value is something that we call statistically significant. So if this was the only association studied, then it would be statistically significant because the p-value is less than 5%. But typically when we're doing market basket analysis, we're looking at all of the rules that we've generated. And just by, coincidence, there's going to be some sort of fortuitous alignment of different items and carts that's going to make it look like there's a pretty sizable lift going on between the products. So we're going to find rules that have a fairly high lift just by random chance eventually if we look at enough rules. So how do we take that into account? Well, we change our thresholds for significance. So what we do is we take that 5% value and we divide by the total number of rules that we're considering. So in this case, if this was the highest lift out of 5,000 different rules that have been considered, well, our real threshold for significance would be 0.00001. So if bottled water was the item that yielded the largest lift with this product, and it was the largest of 5,000 different lifts, then this lift would actually not be considered statistically significant. Because it is greater than our old threshold divided by the number of rules we've looked at, which is 0.0001. So just because after we look at enough rules, we're going to find, a really large lift just by coincidence here, we need to adjust this p-value that we consider, or this threshold that we consider statistically significant. All right.